Hello everyone, welcome to a lecture on microprocessor systems and interfacing. My name is Dr. Vilayat Khan. In this lecture, I will talk about different computer data formats. We need data formats to represent and store data in the computer memory and to evaluate them using computer. For the computer to store the data in memory and to operate on it, the data must be represented in the binary using different codes. And in this lecture, the most popular codes that we would be using during the entire course will be discussed in this lecture. These are the popular computer data formats that we need to understand to understand different concepts of computer systems and interfacing. ASCII is a format, a 7-bit, and then extended ASCII is an 8-bit format. American Standard Code for Information Interchange. BCH is binary coded hexadecimal, which is a 4-bit code to represent decimal hexadecimal digits of the numbers represented using hexadecimal number system. BCD is binary coded decimal. This is a 4-bit code for every digit of the BCD system. Sorry, the decimal system. So every digit of the decimal system is represented using a 4-bit code, and that 4-bit code is called BCD, binary coded decimal. Then we need other format for storing or representing signed and unsigned integers. This can be 8-bit data, it can be 16-bit, 32-bit, and so on. And then we need real numbers to store them in computers and then to operate on them. In coming slides, I will talk about each of these data formats in further detail. Binary coded hexadecimal codes are given in the table here. Here we have a hexadecimal digit. In the hexadecimal system, we have 16 digits, which include digits from 0 to 9, which are actually the digits from decimal system. And as we know that there are 16 digits in hexadecimal system, then the rest of digits are taken from the English letters. A to F, these 6 letters are taken from the English, so we have 16 digits. To store or to represent each of these digits, we need 4-bit. So they are assigned, each of these digits is assigned a 4-bit code, which is called binary coded hexadecimal code. So BCH code is a 4-bit code. These 4-bit are assigned to them in a proper order. For example, just convert these digits 0 to 9 by considering them a decimal number and divide them by 2, just convert them to binary. And if a binary value that we get here by converting this decimal number to a binary, if it is less than 4-bit, then just append zeros on the left hand side to make them 4-bit. For example, if we convert 4 to a binary, we will get 100. So we just append 10 on the left hand side to make it a 4-bit code. We do this for the digits from 0 to 9 as by considering them a decimal number and then converting them to a binary code. So you would get binary coded hexadecimal. For the rest of digits, A, B, C, D, E, and F, just consider them as decimal numbers starting with 10. Until 9, we have digits from 0 to 9 here, and then A is considered as to be 10, B is 11, and finally F as 15, and then convert them to binary, and we will get these codes. So these are 16 codes, and for the 16 hexadecimal digits. Now we can see some examples here. For example, this is a number 2AC is a hexadecimal number, and this hexadecimal number can be encoded using BCH code. So 2, the code for 2 is 0010. So 0010 is written for 2. For A, the code is 1010. So we write 1010 for A, and then we write 1100 for C. So this is the binary coded hexadecimal number, and this is hexadecimal number. Similarly, we can do the other way around by converting a binary number to a hexadecimal number just using the BCH code. So this is a binary number with a decimal point. Just group them into 4-bit group, and each group is assigned a hexadecimal digit according to this table. For example, 100 is 8 in this table, 1000 is 8, and similarly just assign each group of 4 bits a hexadecimal digit, and we would get 83D.E. So this is the hexadecimal number using the represented as are converted using binary coded hexadecimal code. Similarly, we have binary coded decimal codes, which are again 4-bit code to represent decimal digits, digits of the decimal system. As we know, there are 10 digits in the decimal system, so just 4 bits are sufficient to store each of the digit of the decimal system. So each digit of the decimal system is assigned a 4-bit code, and that 4-bit code is exactly the same as the first 10 digit of the binary coded hexadecimal. Here in the binary coded hexadecimal, 0 to 9 digits are converted to binary, and additional zeros are appended at the left side to make them a group of 4 bits. So 0 to 9 are the digits in the decimal system, and these are the code in binary coded hexadecimal. So just use them, and this would make the BCD. So in BCD, every digit is represented using a 4-bit code. It is difficult to remember. It is just easy to convert every digit by considering it a decimal number and just convert it to a binary using the conversions from decimal to binary. And if it is not a 4-bit sequence, then just add additional bits at the left side to make them 4-bit group for each digit. So there is a 4-bit code for every digit of the decimal system, and that code is called BCD, binary coded decimal. Then in binary coded decimal, we can assign a 4-bit code to each, or we can assign an 8-bit code to each digit, and by that we can group them as fact BCD data, where we store as 2 digits per byte. So 2 digits are stored in a single byte, and an unfact BCD, it stores 1 digit per byte. Here we can see example of fact and unfact BCD. 1, 2 is a decimal number, so 1 is here. 1 is assigned a 4-bit code from the BCD, which is 001, and 2 is assigned 0010. So this is fact BCD. And the same number can be stored as an unfact BCD, where this 1 is assigned an 8-bit BCD code. So again, we have the same 4-bit code, but we just assign 4 additional zeros to make it in a byte. So single digit is stored as a byte, and then the second digit is stored as a byte, where the 4-bit BCD code is here, 0010, and some additional zeros are attached here. So in fact, we need less memory, and unfact, we need more memory. So there are some other examples. For example, 6 to 3, each digit is assigned a single, each digit is stored as a byte. So we have 3 digit here, 3 is here, 2 is here, 6 is here, and this is a byte, and this is 4 bits, so we just need additional zeros. So a kind of in converting by storing a 3-digit decimal number, we need 2 bytes. So the 2 and 3 are stored as a fact BCD, and the 6 is stored as a unfact BCD, because this number of digits and this are odd, so we cannot group them by storing two digits in a single byte. In fact BCD and unfact BCD they are almost similar. Just we need one digit. In fact, one decimal digit is stored as a 4-bit code, and two digits are combined in a single byte. In a single byte storage, two digits are stored, while in the unfact BCD, single digit is stored in a 1-byte memory. Then we need ASCII code, which is very popular in using in different programming languages. American Standard Code for Information Interchange. It's a 7-bit code, alphanumeric 7-bit code. Here in this table, which is not a complete table, here we have different letters, English letters, symbols, special characters, uppercase letters, lowercase letters, organized in rows and columns. So each code is a 7-bit code, and to get the code of a symbol or a letter, for example, if you want to get the code for A, uppercase A, then we take the first row here. So A is located in the 4th row, 4x, and X means that the second letter is taken from the column. So A is located in the first column. So 4 is the first letter, 1 is the second letter. So 41 hexadecimal means 41H is the ASCII code for A. So 41H is the ASCII code for A, and when we convert 41 to binary, because 41 is in hexadecimal, so when we convert this to binary, 4 is 0 1 0 0 and 1 is 0 0 0 1. So this is the ASCII code for letter A. And there is an extended version of ASCII code that is called extended ASCII. It's an 8-bit ASCII code. Here we have a parity bit, an additional parity bit plus 7-bit ASCII. In extended ASCII, the character set is it includes some foreign letters, punctuation, Greek letters, mathematical characters, some box drawings characters, and many other special characters. The table is here, and the code for each letter can be interpreted just like the previous ASCII code. Just locate the letter and take the first letter from the row, and then take the second letter from the column, and just convert them to binary using binary coded hexadecimal. We need to store signed and unsigned integers. They can be stored using byte-sized data, word-sized data, or double word-sized data. To store 8-bit unsigned number, we need 8-bit, and the range of an unsigned integer, 8-bit integer, is 0 to 255, or in the hexadecimal it is 00H till FFH. So it means that as a 8-bit unsigned number, we can store any decimal number from 0 to 255. For example, 128 can be stored as an 8-bit unsigned number. Similarly, 8-bit signed number can be stored in 8-bit data or byte-sized data, and the range of 8-bit signed number is -128 till +127, and in the hexadecimal it is 80 till 7FH. So for example, if I want to store +127, I can store it as an 8-bit signed number, but if I want to store +128, I cannot store it as an 8-bit signed number, because it is outside the range of this 8-bit signed numbers, which is given here. Here we can assign weights to each bit here. These are the binary weights. We have 8-bit, unsigned, byte, and in this unsigned byte, there is a weight for each bit position. For example, this is the first bit position, so 2 raised to power 0. As each number here is in the binary formats, we are using the binary system, which is base 2. So this is the position 2 raised to power 0, which is 1, 2 raised to power 1, which is 2, 2 raised to power 2, 2 raised to power 3, 2 raised to power 4, 2 raised to power 5, 2 raised to power 6, and 2 raised to power 7, which is 128. So these are the weights. And for the sign byte, the same weights are used except the last weight, which is minus 128. So if you want to store a number here, then the binary number is put here, and each bit is multiplied with the corresponding weight, and the value is calculated. And that value is the binary representation of the decimal value that we would get by multiplying these weights with the corresponding bit and then adding them. And the same procedure is applied here by considering this last weight as minus 128. So this is the representation of byte-sized data using 8-bit unsigned number and 8-bit signed number. If we need to store larger data, then we need 16-bit unsigned and unsigned and signed integers. We need 2-byte data, or we can say word-sized data. So this is an example of byte-sized data where +8 is stored here. +8 is converted into binary, which is 000100, and we can convert it to 2's complements by first taking 1's complement, and 1's complement if a binary number is taken by inverting each bit. So this is +8, the binary representation of 8. And if we want to represent this +8 or represent -8, then we have to take the 1's complement of this number, and by 1's complement we mean that we have to invert each bit. So by inverting each bit of this number, we get this number, which is the 1's complement of this input. And by adding 1 with this 1's complement, we get 2's complement, and 2's complements of a number is the negative number of that original number. So we had +8, and when we got the 2's complement of this number, we got the -8 here. So these are the signed numbers. We are the this is the -8, where the sign is minus, and we can store them by just putting these bits in the byte unsigned, the signed numbers 8-byte boxes in the previous slide, like here. So just put these bits in this position, and when we multiply these binary weights, we will get the same number -8. 2's complement can be directly computed from the input number. For example, the same number is here, 000100. So we can compute 2's complement directly by keeping all the digits until the first non-zero bit and inverting the bits after it. For example, we have 001000. So start from the right hand side or start from the least significant bit and keep the digits until the first non-zero digit. So in this case, we keep the digits until the first non-zero digit, which is 1 here at the 4th position. So we keep 0, 0, 1 at the unchanged. We keep them unchanged, and then all the bits after this are inverted. So we in this case have 0, 0, 0. So we invert them. So we get 1, 1, 1, 1, 0, 0 is the 2's complement of that number. So 2's complement can be computed either by taking 1's complement and then adding 1 at the least significant position, or directly by keeping all the bits until the first non-zero digit is unchanged and then inverting the rest of the digits on the left position. If we need to store a larger data, we need word size data. In the word size data, we need 16 bits. And the same procedure is applied to assign them weights. So these are the weights. Until the 128, we have the same weights. This is unsigned word, and after 128, we just continue like we did for the byte size data. Here we had 2 raised to power 7. Here we have 2 raised to power 8, which is equal to 256. And at the end, we have 2 raised to power 15, which is 32,768. So this is unsigned word, and the last weight is plus. And if we would be using signed word, then the last weight, binary weight, would be minus 32,768. And the rest of the procedure is the same. Here we introduce a new concept, which is little endian and big endian. As we have 2 bytes, and the memory is normally organized as a single 1 byte for location. So let's suppose this is the memory, a computer memory, and the addresses increases when we go up. So this is 2FFH, H means hexadecimal, so this value is in the hexadecimal. This is actually a 16-bit memory address. And then the next address when we go up is 300H, then the next one is 3001, and the next one is 3002. So let's suppose we have a value, word-sized 16-bit value, 1234H. So this is the hexadecimal 16-bit value. If we want to store this value in the memory, then 2 approaches can be used. Either 12 is the most significant byte, 34 is the least significant byte. If the least significant byte is stored in the lower address, 300 is the lower address, 3001 is the upper address or higher address. So if the least significant byte, which is 34 in this case, is stored in the lower memory location, then this is called little endian. And if the least significant byte is stored in the upper memory address, then it is called big endian. Normally computers use little endian format. So little endian, in the little endian, least significant byte goes to the lower position, and the most significant byte goes to the upper position. And in the big endian, it is the reverse. So these are the least little endian and big endian concepts, which are and simple to understand. Okay, so in the double word size data, we need 32-bit or 4 bytes of data, and the same procedure is followed for the binary weights. Just continue with the 2 raised to power the bit position. For example, until 15, we had 2 raised to power 15 for this value, and then we continue with 2 raised to power 16, and at the end we have 2 raised to power 31. This is unsigned double word. For the signed double word, the last weight would be minus. The same little endian and big endian concept is here. The lowest lower order byte goes to the lowest position memory location, then it is little endian. For example, 1, 2, 3, 4, 5, 6, 7, 8, H. This is a 4-byte value represented in hexadecimal. If we want to store it, then using the little endian approach, we would store the least significant byte, which is 7, 8 in this case, is stored in the lowest memory location, and then the upper byte is stored in the upper memory location, and so on and so forth. So little endian approach is used here. Real numbers, to store real numbers or floating point numbers, they can be stored as a single precision format, which is a 4-byte or 32-bit format, and real numbers can also be stored as a double precision, which is 8-byte or 64-bit format. Single precision, some significant bits or significant digits are lost, while in the double precision, more digits after the decimal point are stored. So, and the single precision, which is a 32-bit format, given here, we need 23 bits for the significant to store, and we need 8 bits for the exponent to store, and one last bit is assigned for the sign of the real number. If it is plus sign, then a 0 is used here, and if it is a negative sign, then a 1 is used here. So this is the sign bit, a single bit which represent the sign of the real number. To store a real number, we must represent that real number in the normalized form, and in the normalized form there is a digit on the left hand side of the exponent, which is normally 1, and there is a fraction or significant part of that real number which is after the decimal point, and then there is a base which is 2 in the binary system, and there is an exponent. So we do not store the base because it is always known, and we do not store the digit after the on the left hand side of the decimal point, which is always 1. And in the binary system it is always 1. And to store the exponent, an 8-bit data is used here in this 32-bit format, and 23 bits are used to store the significant of the real number. And in the double precision in 8-bit or 8-byte or 64-bit double precision format, bits from 0 to 51, which becomes total bits are 52, they're assigned to significant, while bits from 52 till 62, which are 11 bits, they're assigned to exponent, and the last bit is assigned for the symbol or the sign of the real number. So let me okay, so for the sign bit, in the single precision, there is sign bit, 8-bit exponent, and 23-bit fraction or mantissa. 23-bit is used to store the mantissa or the fraction. Mantissa, there is an implied hidden 1-bit, which I just mentioned, plus 23-bit. The 1-bit is the bit on the left-hand side of the decimal digit, which is hidden and not stored here. This is normally the first bit of normalized real number, and the exponent is stored as a biased exponent, which means that the exponent is added with 7fh, which is a number 127 in decimal, and this value is added with the exponent. So here we have a typo. This is not mantissa, but the exponent. The 8-bit exponent plus 127 is always added, and the result is then stored in the memory. There are some exceptions. For example, when exponent is 255 and the mantissa is 0, then this is considered to be as infinity. When the exponent is 0, m is 0, then the number is 0. When exponent is 255, m is not 0, then this is not a valid number. And if exponent is 0 and mantissa is not 0, then this is not in the normalized form. We have to convert it to normalized form. Here are some examples where we have single precision real numbers. By single precision we mean 32-bit or 4-byte real numbers. So we have a decimal number plus 1 2, and we can store this plus 1 2 as a 32-bit single precision real number in the computer. So to convert this plus 1 2 to a real number, binary real number, then we have to represent this 1 2, or to convert this 1 2 to a binary by just converting as we did, as we know, by dividing it with 2, base 2. So just convert them to a binary numbers. 1 2, when converted to binary, it becomes 1 1 0 0. So this is a 4-bit binary number, and then this binary number is normalized where a decimal point is introduced. So after normalizing, we would get 1.1 multiplied or cross 2 raised to power 3, because we moved the decimal point from here 3 position on the left hand side. So we would get a normalized form which is equal to 1.1 cross 2 raised to power 3. So this is the normalized form of this binary representation. So what we do, first convert this number 1 2 to binary, then convert it to normalized form, and then we can create or generate the bits of the 32-bit data. So as we have plus sign, so the sign bit is 0, and we have the exponent which is 3, and 3 in the binary is equal to 0 0 0 and finally 1 1, and 127 in the decimal, or 7fh as added with this 3, and at the end we get 1 0 0 0 0 1 0. So this is the biased exponent which is stored in that 8-bit location, 8-bit part of the 32-bit real numbers. And then to fill the rest of 23 bits, this mantissa, which is here, this part, the digits after the decimal point, are stored in this 23-bit part of the mantissa. This bit is here, and the rest of the bits are just filled with zeros. If there are no more non-zero bits, then they are filled with zeros. So let me show you another example where we have -12. So the same procedure is followed, just we have the sign bit is 1, the rest of the values are exactly the same. Here we have plus 100. So this 100 is converted to a binary value just by dividing it with 2. So we will get this 7-bit value, which is 1100,100. So this 7-bit value is the binary representation of this decimal value 100. And after normalizing it, we move the decimal point 6 position on the left hand side to tell here. So we would get 1.1001 into 2 raised to power 6. So this is the normalized representation of this decimal value. So in this case, as the number is a positive number, so the sign bit is 0, and we can now represent this exponent as the biased exponent, which is here. And this biased exponent, let me do this calculation for this to understand how to get the biased exponents. So first we represent this 6 as the binary number, as an 8-bit binary number. So 6 is equal to 0000110. So this 6 is the binary representation of, this is the binary representation, 8-bit binary representation of decimal value 6. After doing this step, we add 7FH with this value. 7FH in the hexadecimal is equal to 01111 and then 1111 in the binary. So we just add them. So by adding them, you would get 0 plus 1 is 1, 1 plus 1 is 1, 0. So 0 is here, and 1 is the carry till next position. So we get 1 here, then 1 plus 1 plus 1. So we get 1, 1. So 1 is the sum, and 1 again is the carry for the next position. So we continue this and we get this value. And this is the biased exponent, which is here, 100000101. So this is the biased exponent. So we have just calculated the biased exponent, 8-bit biased exponent for the 32-bit real number. And then we get the mantissa here, which is 1001. So 1001 is written here, and the rest of the bits of the 23-bit mantissa are just filled with zeros. So this is this 32-bit value, this 32-bit data actually is representing plus 100. So when we store this value in the computer memory, this actually represents the real number plus 100. This can be extended with other examples. For example, minus 1.75. This is again very simple. We just have to convert this 1.75 to binary number by first converting the integer part to binary, and then converting the fraction part, which is 0.75 to binary, and then combining both of them, and we would get 1.11 in the binary. So this 1.11 is then normalized, and we would get 1.11 across 2 raised to power 0. And the symbol is minus, so we will assign 1 to the sign bit, and then we have 0, so just add 7FH, which is 01111, and then 4 ones. So when adding that value 7FH with 0, we would get the same value 7F here. And mantissa is 1 1, so we get 1 1 here, and the rest of bits are filled with zeros. And so this is 32-bit single precision real number, which is minus 1.75. And there we can continue with many more examples. For example, plus 0.25. When converted to binary, we would get 0.01. So this is 1.0 into 2 raised to power minus 2, and then we can continue with the same procedure, and we would get the 32-bit real number here. These are the popular data formats that can be used to represent data, real numbers, signed and unsigned integers, binary coded hexadecimal. We can represent just decimal numbers using BCD. We can represent hexadecimal numbers using binary coded hexadecimal, and we can represent them, we can store them in the computer, and we can operate on them using a computer microprocessor of the computer. If there are any questions or queries while you are watching this lecture, please keep a note of them, and you can ask those questions and queries during the online session. Thank you.